Okay, so when we left off on Tuesday, we were talking about velocity, frequencies, and the wavelength. Okay, and then we started talking about standing waves. Okay, and how if you have a certain frequency, okay, a wave will have, what's the wind? Will have constructive and deconstructive interference back and forth, which can create an illusion of a standing wave, in which the wave seems like it's standing still. So we're going to kind of build off of that. Okay, we're going to look at how these standing waves work with instruments, such as a guitar for a string instrument, or a flute, or a recorder for a air instrument. Okay, so here we have some standing waves here. So you can see one example, the second example, and the third example. Okay, so everything's going to be built off this equation here. So the frequency is going to be the velocity divided by the wavelength. Okay, and then based off the standing wave, we're going to look at how we can rewrite this equation. Okay, here we have the length of the string for each one. Okay, or the length being the same, and that's indicated in orange. I know the drawing isn't perfect, but assume that the length for all three of these examples are the exact same. Let me add in some dotted lines here for the middle. All right, so we have the frequency, okay, for the first one. This could equal the velocity divided by 2L. Now 2 times the length, okay, for our first one, let me indicate number 1 here. We'll go 1 right here, 2, and 3. Okay, so the length here for number 1 is only a wavelength. Okay, so let me go wavelength here. The length equals 1/2 wavelength. Okay, so 2L will equal the wavelength. Okay, now if we plug that number in for wavelength at the bottom of the equation, we get the frequency. Okay, in this first example is going to be the velocity divided by 2 times the length. Okay, so that's highlighted there in green, in the green highlighter. That's where we get that equation. The length, okay, is 1/2 of a wavelength. Okay, so therefore the 2 times the length of the string is going to be the wavelength. In our second example here, okay, we have a standing wave. Okay, and now the standing wave, okay, we have 1 full wavelength. Okay, in this example, so we have 1 full wavelength. Okay, so wavelength equals L, giving us the equation here in green. The frequency is going to be the velocity of that wave divided by the length of that wave. Okay, here we simply substitute length for the wavelength, because the wavelength is the length of the string. Okay, after that, our third one is a little bit trickier. Okay, so our third one, actually I wrote this one out in green previously, is going to be, we see 3, okay, 3/2 wavelengths. Okay, so if you notice here, let me go in purple, we have 1 full wavelength here, and then we have a 1/2 wavelength here. Okay, so we have 1.5 wavelengths total. Okay, and that's where you have here. So we have 3/2 wavelengths. Okay, is going to be the distance. Okay, so 1.5 wavelengths is going to be the length of the string. Okay, so if we rearrange that to 5, the wavelength is going to be 2 times the length divided by 3. Okay, so 2 times the length divided by 3 is going to be the wavelength in this scenario. So we plug that in our frequency equation. Frequency equals velocity divided by 2 times the length divided by 3. Okay, that 3 at the bottom here, okay, actually moves to the top of the fraction, giving us the equation here, being frequency equals 3 times the velocity divided by 2 times the length. Okay. Now, go back here. So, that's how we kind of came to the equation all in the green there. Okay, the highlighted green equations. The first one is V divided by 2L. The second one is V divided by L. The third one is 3 times velocity divided by 2 times the length. So, what we can do here, okay, is if we rearrange these green equations, okay, as we did in the pink, okay, we're going to see a pattern. Okay, so in the first one, if we rearrange this as a pink, okay, this is frequency 1 times 1 times velocity over 2L. Number 2 is 2 times V over 2L. And for our third one is 3 times V over 2L. So they all have the same pattern. Okay, and what these are called harmonics. Okay, so we have the first harmonic, the second harmonic, and the third harmonic for standing waves. Okay, so that's where we got our pink equations. Okay, those are going to be our harmonics. Okay, now those can be written out as a full equation here. So F times the number. So you see in the pink I wrote, F1, F2, F3. Okay, F times that number harmonic, okay, N is going to be the harmonic number, is going to be equal to that N number, okay, whether that's 1, 2, 3, 4, it has to be an integer, a full number, can't be a decimal. Okay, is going to equal the number times the velocity divided by 2L. And that's going to be our base equation for our harmonics. Okay, and again, indicating N is going to be the harmonic number. Okay, full integer, 1, 2, 3, 4, 5, 6, and on and on and on. Okay, so that's for a stringed instrument. Okay, just picking up where we're off. Now, if we want to look at an open pipe instrument, an open pipe is going to be openings at both ends of the pipe. Okay, openings at both ends. Okay, so if we look here, the equation for an open pipe instrument, looking at the harmonics for standing waves, is going to be the same. Okay, the equation is going to be the same as here in the pink. So F times the harmonic number, okay, or F of the harmonic number is going to equal that harmonic number integer here, okay, multiplied by velocity divided by 2 times the length of that pipe. Okay, the only difference for an open pipe instrument is the pictures are now inverted. Okay, so if we want to compare, okay, the first harmonic here, okay, notice that the antinode is in the middle and the 2 nodes are on the outside. So I'll try to do that. So we have the antinode here, and we have node, and we have node. Let me do a different color. We'll do pink for the antinodes. And we'll do, what color haven't I used? Blue. For nodes. And a node here. So in our first harmonic on a string, notice that the antinode is in the middle and there are 2 nodes on the outside. In an open pipe, it's flipped. We have a node in the middle and 2 antinodes at the end of the pipe. Okay, for our second harmonic in an open pipe, we have antinode at the ends, and we notice 1 in the middle. So 3 antinodes with 2 nodes. Okay, in our third harmonic, we have 3 nodes, 1, 2, 3, with 4 antinodes. 1, 2, 3, 4. So we already compared 1, so if we go to 2, again, we have 2 nodes and 3 antinodes. On the string, we have 3 nodes and 2 antinodes. Okay, so those pictures and the visual of the standing wave is just inverted. Okay, if we go to number 3, okay, we have 4 nodes and 3 antinodes. Now, if we look at the third harmonic in a wind or an open pipe instrument, okay, or open-ended instrument, we have 4 antinodes and 3 nodes. Lastly, on a closed pipe instrument, it's going to be slightly different. Okay, so here's our first harmonic. okay, is simply a node at the end by the closed end of the pipe, okay, and an antinode at the end. Okay, so if we look at these equations, it's going to be very similar, okay, but instead of using N, we're going to use M. Okay, and I'll touch on that in a second. So M, for whatever harmonic that is, times the velocity, but instead of divided by 2 times the length, it's going to be divided by 4 by the length. Because if we look at the first one, okay, our first visualization, our first standing wave is 1/4 of a wavelength. Okay, that's only 1/4 of a wavelength. Okay, so that's where we're going to get divided by 4 times the length. Okay, now the M for closed pipe instruments, harmonics only come in odd numbers. Okay, that's why if you look here, we have the first harmonic for a closed pipe, we have the third harmonic for a closed pipe, and we have the fifth. Okay, so again, notice there's always a node at the closed end. Okay, oh my god, that was writing A's. Node, node, and then there's a couple other nodes within that. Antinode here, antinode at the end, always an antinode at the end of the pipe, and a node at the closed end of the pipe. Okay, an example of a closed-ended pipe instrument would be an organ. Okay, so that is it. So these are the equations. For a closed pipe, you're going to need Fm equals M times velocity divided by 4L, and again, that M is has to be an odd integer. Okay, for an open-ended instrument or open-ended pipe instrument, okay, open-ended is going to be Fn. Okay, N is simply the harmonic number, so the harmonic frequency, okay, is going to equal that number times the velocity divided by 2 times the length of that string or pipe. Okay, and that same for string instruments, that's going to be the same as well. Okay, we already went over Doppler effect and other things, so that is all. That is the rest of the lesson, building off a Tuesday that we didn't get to. Okay, if we have any questions, we're going to review all of waves sounds as well before the test. Okay.